All right, so for this part, I'm going to show you, I'm not going to go all the way through it, but because this might be, I actually myself haven't watched the last 20 minutes of Grant's video. So this might be a preview of what he's talking about, but this is what we did in the project from Ingenuity in Mathematics. Okay. When we look at a large circle, and we want to count up all the lattice points that are inside it, and why would we want to count up the lattice points that are inside of it?
Well, it's the area.
Yeah, so the number of lattice points,
It's an approximation for the area.
is approximately equal to the area. Okay, so if this is, if the radius is n, so we know the area is pi n squared, and it's also approximately equal to the number of lattice points. Now there are going to be some lattice points that are just inside the circle and some lattice points that are just outside the circle.
So they're not inside. These are inside, but
Yeah, and that's why this is just an approximation, because we're going to have we can put little boxes around those lattice points.
yeah.
And sometimes that box is going to add in a little bit of extra area. Sometimes a box might miss.
Some.
So it's gonna.
Well, actually, sorry.
balance out.
So sometimes a box around this other lattice point that we're not counting is going to be part of the circle. So we're not going to be counting this area, but we'll be counting this area outside. And that's why it's just an approximation.
Yeah.
But it should balance itself out reasonably well.
Yeah, your intuition would say that this at least as n gets large, you might start thinking that the area I count on the outside and the area I miss on the inside somehow start to balance each other out. And this becomes a better and better approximation. Now, the number of lattice points inside is always going to be an integer. Why?
Well, because there can't be like half a lattice point inside the circle.
Right. Is the area ever going to be an integer? Is pi times an integer ever going to be an integer?
No.
No.
Why not?
Pi is not an integer.
Pi is irrational.
Pi, but not only is pi not an integer, it's not a rational number, it's not a ratio of two integers. So by counting, no matter how big the circle gets, counting the lattice points is never going to be exactly equal to the area. And it's always just going to be an approximation. But it'll be a better and better approximation to the area. And the number of lattice points divided by n squared is going to be a better and better approximation for pi.
Yeah.
Right?
Yep.
Yeah.
Okay.
Going to be.
So that's actually kind of a cool way to approximate pi if you had a big circle. But the lattice points also represent something that we've been looking at. Okay. The lattice points are the number of each lattice point represents a x squared plus y squared equals some integer squared for m less than or equal to n. Okay, so our circle has radius n. Mm-hmm. Each lattice point represents some integer so that we could sum the squares and get that square.
Okay.
Right? So we get the number of ways to write m. Do I want to say m or m squared? Actually, I want to say m. Write m
Yeah.
as the sum of squares. Remember, 0, there was one way to do it.
And then 1.
So the number of ways to write 0, I'll call this, I gotta make up a function for this, so I'll call this writing m. So the number of ways to write 0 was
1.
1. The number of ways to write 1 was
4.
4. Okay, we do that, so we get w of 0 plus w of 1 plus w of 2 all the way up to w of n. That's the number of lattice points.
Yeah.
Right?
Yeah.
Right?
Cool.
N was the radius of our circle. Right?
Mm-hmm.
Yeah.
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 And then that's just like the rings.
Right, those are the rings.
Those are how many lattice points touch all the rings inside the circle. So
Yeah.
you'll get them all.
That's right.
Yeah.
You will get them all. So, summing up the number of ways to write each integer as a sum of squares somehow gives you a way to approximate pi, which is really crazy, huh?
Yeah.
Okay. In fact, when I take the average of this, the average number of ways to write a number as a sum of squares. Remember, there was one way to do it for 0, 4 ways to do it with 1. You said a couple had 8, but we saw lots of them had 0 also.
Yeah.
Yeah.
When I take the average here, what do you think I get
Pi.
as n goes to infinity?
Pi.
Pi.
Wow.
Cool.
Yeah, really cool. And so that's what Grant's going to be talking about.
Yeah.
Or at least, I think he's actually going to prove a more complicated formula. But the average number of ways to write an integer as a sum of squares, sum of 2 squares, is pi. Crazy.
Cool.
All right. Good work this morning, guys.